Hi, everyone, and welcome to today's lecture on infrared spectroscopy. Whether you're a student, a researcher, or just curious about how we analyze chemical materials, you're in the right place. Today, we'll dive deep into the two main types of IR spectroscopy, dispersive IR and FTIR. By the end of this video, you'll understand their principles, advantages, limitations, and where each technique shines. Let's get started. Infrared, or IR, spectroscopy is a fascinating analytical technique. It allows us to identify molecular components and understand their chemical properties by observing how they interact with infrared light. This process reveals a lot about functional groups, chemical bonding, and even the material properties of a sample. But why is infrared light so special? It is because the energy in IR light matches the vibrations of chemical bonds in molecules. When the light interacts with a sample, the bonds absorb specific wavelengths, giving us a unique molecular fingerprint. Now, let's explore how dispersive infrared spectroscopy works. This method relies on a device called a monochromator, which separates infrared radiation into individual wavelengths. The detector then measures the intensity of light absorbed by the sample at each wavelength, and this data is used to produce a spectrum. However, there is one important consideration. Because the system scans through the wavelengths one at a time, it takes longer to acquire all the necessary data. This sequential scanning process is what makes dispersive IR a bit slower compared to other modern techniques. Dispersive IR spectroscopy has its own unique set of advantages, making it a valuable tool for certain applications. First, it is well suited for routine and simple analytical tasks. If your analysis doesn't require highly complex measurements, dispersive IR can be a great option. Second, it can provide good resolution for specific types of samples, making it effective for certain targeted analyses. Lastly, the operation is often simpler compared to more advanced systems. With basic functionalities, it's straightforward and user-friendly for those conducting standard analyses. While dispersive IR spectroscopy has its strengths, it is important to acknowledge some limitations that come with this technique. First, time consumption is a key drawback. Since the method scans wavelengths sequentially, data acquisition can be quite slow compared to modern alternatives. Second, it has a lower signal-to-noise ratio. This means the data can sometimes be less precise or harder to interpret, especially for samples with weak signals. Lastly, the technique involves moving parts like monochromators, which can introduce mechanical complexity and may require frequent maintenance to ensure accuracy. Understanding these limitations helps us decide when dispersive IR is the right tool for the job and when we might need to consider alternatives. Now, let's talk about Fourier Transform Infrared Spectroscopy, or FTIR, is a revolutionary advancement in the field of infrared spectroscopy. FTIR relies on a powerful instrument called an interferometer, specifically the Michelson interferometer. Here is how it works. The interferometer modulates infrared light by splitting it into two beams and then recombining them. This creates a signal called an interferogram. What makes FTIR special is the speed and precision with which it processes data. Instead of scanning one wavelength at a time, FTIR captures all the infrared wavelengths simultaneously. This raw interferogram is then processed mathematically using Fourier Transform to generate the IR spectrum we use for analysis. With FTIR, we get faster data acquisition, improved sensitivity, and higher resolution, making it a go-to method for modern laboratories. FTIR spectroscopy operates using a clever and efficient system, the interferometer. Here's the process. The interferometer splits a single beam of infrared light into two paths. These beams are then recombined to create an interference pattern. known as an interferogram. What makes this technique so powerful is that the interferogram contains information from all wavelengths simultaneously. Rather than analyzing one wavelength at a time, FTIR collects everything at once. The final step is a mathematical process called Fourier Transform, which converts the interferogram into a usable spectrum. This spectrum provides the detailed molecular fingerprint we need for analysis, quickly and with precision. Fourier Transform Infrared Spectroscopy, or FTIR, has revolutionized the way we analyze materials, and here are some of its standout advantages. First, rapid data collection. Unlike traditional techniques, FTIR measures all wavelengths simultaneously, dramatically speeding up the process. This makes it ideal for high-throughput labs and time-sensitive analyses. Second, FTIR offers high sensitivity and an excellent signal-to-noise ratio. This makes it perfect for detecting weak signals and analyzing even trace amounts of a substance with precision. Finally, FTIR shines in its versatility. It's compatible with a broad range of sample types, from gases to liquids to solids, making it a go-to method for diverse applications across industries. With these advantages, it's no wonder FTIR has become an essential tool for modern spectroscopic analysis. While FTIR is an incredibly powerful tool for identifying molecular structures and characterizing materials, it does have a few limitations that we need to consider. So, let's break them down. First up, computational processing for the Fourier transform. Now, FTIR works by measuring the absorption of infrared light by a sample and generating a spectrum. However, the raw data collected by the instrument is not directly interpretable. The Fourier transform is a mathematical process that converts the raw time domain data into the frequency domain data we use to generate the final spectrum. This means that FTIR requires specialized computational processing, which adds a layer of complexity. Without the proper algorithm or computational power, interpreting the spectra can be difficult. So, if you're not familiar with the process, it might take a little bit of time to get used to. Let's quickly compare two popular infrared spectroscopy techniques, dispersive IR spectroscopy and FTIR spectroscopy. We'll break it down feature by feature so you can see why FTIR has become the go-to choice for modern labs. Section 1. Methodology and Speed. Dispersive IR uses a monochromator to isolate and scan individual wavelengths one at a time, which makes it slower. FTIR, on the other hand, uses an interferometer to collect data from all wavelengths simultaneously, giving it a huge speed advantage. Section 2. Signal-to-noise ratio and resolution. When it comes to signal-to-noise ratio, FTIR is better because it collects all wavelengths at once and averages signals. And for resolution, dispersive IR is limited by the monochromator's capability, while FTIR offers higher adjustable resolution thanks to its advanced setup. Section 3. Complexity and Maintenance. Dispersive IR is mechanically more complex because it relies on moving parts, which also makes it more costly to maintain. FTIR has fewer moving parts, making it simpler and more economical in the long run. Section 4. Versatility and Applications. FTIR is far more versatile. It works better for weak signals and can handle a wider variety of samples, solids, liquids, and gases. Dispersive IR, while useful in some cases, is older technology and less commonly used today. So, to sum it up, FTIR is faster, more sensitive, versatile, and easier to maintain. While dispersive IR has its place, FTIR is the preferred choice for most modern research and industry applications. Now let's talk about the practical applications of FTIR spectroscopy. Here are three key ways this technology is commonly used in research and industry. Point 1. Identification of functional groups. First, FTIR is widely used for the identification of functional groups in simple organic compounds. By analyzing the absorption of infrared light, it helps scientists pinpoint the specific chemical bonds and molecular structures in a sample. Point 2. Industrial analysis. Second, FTIR is invaluable in industries like pharmaceuticals and polymers. It's used for material analysis to ensure the quality and consistency of products, making it a crucial tool in quality control. Point 3. Routine laboratory use. And finally, FTIR is perfect for laboratories with routine infrared analysis needs. Its quick and accurate measurements make it ideal for day-to-day applications across various fields. So, whether it's identifying molecules, analyzing industrial materials, or supporting routine lab work, FTIR is a versatile and essential tool. As we wrap up, let's take a look at the real-world applications of FTIR spectroscopy. It's an incredibly versatile tool used across a wide range of fields. Here are three of its most important applications. First, FTIR is a staple in research laboratories for conducting detailed chemical analyses. Whether it's studying molecular structures or characterizing new compounds, researchers rely on FTIR for its precision and accuracy. Second, FTIR plays a crucial role in environmental and forensic studies. It helps in the identification of unknown substances, whether it's detecting pollutants in the environment or analyzing trace evidence in criminal investigations. And finally, FTIR is essential in industrial applications, particularly for quality control and quality assurance. From pharmaceuticals to polymers, manufacturers use FTIR to ensure their products meet the highest standards. So, whether it's advancing research, solving mysteries, or maintaining industrial standards, FTIR spectroscopy is a powerful tool with applications that truly make an impact. Let's take a moment to highlight the key distinctions between dispersive IR and FTIR spectroscopy. Dispersive IR is slower, mechanically more complex, and less sensitive because it relies on sequential wavelength scanning and older technology. FTIR, on the other hand, is faster, highly sensitive, and has become the preferred tool for most modern analytical applications. Its advanced design makes it ideal for quick and reliable measurements. And finally, FTIR's ability to collect all wavelengths at once is what truly sets it apart. This feature makes it the top choice in laboratories worldwide, whether for research, industrial quality control, or environmental analysis. So, FTIR outshines dispersive IR in speed, sensitivity, and modern applicability, making it the go-to solution for today's spectroscopy needs. Infrared spectroscopy has proven to be an invaluable tool in chemical analysis, offering deep insights into molecular structures and compositions. While dispersive IR spectroscopy is still useful for certain specialized applications, it does come with its limitations, such as slower speed and lower sensitivity. On the other hand, FTIR spectroscopy stands out as the preferred technique for modern analysis. It's faster, highly sensitive, and incredibly versatile, allowing it to adapt to the demands of research, industry, and beyond. With its ability to provide reliable and efficient results, FTIR continues to revolutionize the way we approach chemical analysis, making it an essential tool in today's scientific landscape. Thank you for joining me on this journey through infrared spectroscopy. Keep watching for more insights into analytical techniques. See you next time.